Hi, in this video, we want to take a look at some of the shortcomings of diagnostic plots in linear regression. All right, so diagnostic plots are a great way for us to understand what's going on with our models, for us to go through and see how we can improve our models. Like they can tell us like which observations are the ones that might be problematic. There's a lot of good information there, but they don't tell us like everything. And there's some major shortcomings. So what we're going to look at today is a situation where we have an incorrect model structure. So the mathematical equation that I'm using is not the mathematical equation of the underlying system. And so no matter what I do with my diagnostic plots, there's going to be no indication that of what I should do from the diagnostic plots. I just will be looking at it. I just know something's wrong, and the plots aren't going to tell me how to fix it. All right, so let's go ahead and load the data. All right, so what I'm going to do, I'm going to load it. This is from the ALR 3 package. So this is Applied Linear Regression book, edition 3. And I'm going to sort the data by the target variable. And then I'm going to go ahead and label the I'm going to label the rows by the row number after I've sorted. So what this does, this enables me that when I go through the diagnostic plots and it starts flagging points, I know, hey, does it look like the low target variable values or the high target variable values or middle or something like that? I might be able to spot another issue that's going on because I've set up a more organized data set. And of course, I always color my points by an important variable. And so I'm coloring the points by the target variable. And that's what this code is doing. Now, something that's different this time is that if you go through and you look at the data, you'll go like, hey, the target variable has a lot of significant digits. And if I want to do the coloring, I went ahead and just rounded the values down to 0.1. And so this way, so I round to the decimal, the first decimal place. And then we go ahead and use this part and this part of code to define what the colors are. And so I'm actually coloring by the rounded value, not the value itself, but that's close enough visually for what we're doing. All right, so now let's go ahead and look at the scatter plots. Oh, this did not carry through. All right, so the true thing that's going on is that y is equal to the absolute value of x1, then multiplied by a rational function on x2. Okay, so when I have the x2 portion will shrink things down when I have a large x2 value as I get farther and farther away from the origin because of how it's set up. And this is an error, but no, don't worry about it. Let's delete that. All right, let's go ahead and do the scatter plot. So now when I look at the scatter plot, I can see, like here you can kind of see the absolute value structure, but if this is what was handed to me when I was model building, I wouldn't think absolute value. Honestly, I would probably think x squared, looking at that. Now here, I see that I have like a triangle region, but it's not really obvious to me what do I do to get a good model out of this? Now here, this shows me that x1 and x2 are probably independent of each other because this looks like a cloud. I would lean towards the idea that maybe they're distributed throughout the unit circle, but I don't know. I won't know for certain. All right, let's go ahead and build the model. So I'm just going to build a regular linear term model, and on my data set, I'm going to go ahead and store the standardized residuals. Remember, standardized residuals, it's just like normalizing data, subtract the mean and then divide by the standard deviation. Well, residuals in linear regression always have mean 0, so we're just dividing by the standard deviation, or standard error is what it is. And then here, I'm taking the fitted values and putting it onto my data set. All right, so now let's go ahead and plot the standardized residuals. And right out of the gate, I'm going to plot the residuals with respect to the fitted values. Remember, when I look at residuals, if I see a pattern, that's a problem. All right, so here I see kind of like the residuals spreading out. Now, I should not see a pattern when I look at this. So now, if this was like a predictor variable was along the x-axis, I might consider something like some kind of transform, let's say log transform, square root transform, or maybe work with different weights. But this is the actual fitted values. The fitted values, I'm not going to be changing the fitted values. At least not in linear regression. Now, if I want to do something nonlinear, maybe we might be able to do something better. All right, now let's take a look at the standardized residuals by the observed y value. Now remember, if I see a pattern when I look at residuals, that's a problem. That's a pattern right there, right there, right there, right there, right there. Okay, this is telling me that I have a crap model. This is not a good model. But let me ask you this. How do I fix it? Let's say my job depends on me making a predictive model with that y and those two predictor variables. I'd be in a tough spot, honestly. Now, if I was to somehow figure out that it's absolute value time of x1 times a rational function on x2, then I would have like a lot of, I'd be able to figure out, I'd be able to make a sweet, sweet model. But here, when I look at it, it's not popping out at me. I'm not seeing it. All right, now let's look at the standardized residuals by the first predictor variable. All right, so here I can kind of see like what looks like, to me, that looks more like an x squared, like a very shallow quadratic. So in real life, if I saw this, I would start looking at including an x1 squared term. Now let's look at the standardized residuals by the second predictor variable. And we see a triangular region. Now this doesn't really tell me like what I should try, what would work. You know, like what do you attempt to do? I don't know. Honestly, at this point, I would start looking at the pairs plot, go back up here, and I'd be trying to come up with something that would work based off of this. So I can see that it's like the magnitude of the y decreases as x increases. And so I might want to do something that does maybe like with a, let's say, a +1 and the bottom of a rational function, and then with x2 and square it. Maybe if I got like really lucky on spotting that, but realistically, I probably wouldn't spot it. Let's hop on down. Let's see, where were we? Oh, that's fitted. That's observed. x1, x2. Okay, so I'm really not seeing a whole lot on how to approach this. Oh, that's my dog. All right, so now I'm going to go ahead and plot the standard diagnostic plots. Let's see if that reveals anything to me. All right, so here it's definitely detecting that there's like this horn shape to my residuals, and it's in particular, it doesn't like the larger y values. So that's something I'm spotting because I've colored the points the way I did. I labeled them the way I did. You'll notice that it's like dark, then lighter color, and then lighter and lighter. And I should not see a pattern when I look at my residuals. And now here I've got my normal plot, and I can see that the largest y values are the farthest, are corresponding to the farthest out from the hypothesized distribution. And here, this one, All right, so that, you know, since it's absolute value, square root the absolute value, it's like folding the previous plot on itself. And here it's saying that there's a pattern right there, which is not good. And Cook's distance, all right, so I have a bunch of larger Cook's distance for larger y values, and then the 13th observation is kind of just like popping out. You can see like darker as I go up, it gets lighter, but it's not strong of a pattern as in the other plots. But as I look through this, this always tells me that there's a problem. It doesn't tell me how to fix it. And that's really what I'm trying to drive at with these. All right, so now here's a good rule of thumb, a really good plot to look at when you do multiple linear regression. What you can do, you can plot your fitted values by your observed values. Now, if you have a good model, everything should be close to the line, 0 for the y-intercept, slope 1. So let's go ahead and do that. So I plot the points, and now I plot the line in red that regresses the fitted values onto the observed values, and then I plot the line with y-intercept 0, slope 1. If I have a good model, these two will be close to each other. Let's see what we get. They're not close at all. I mean, down here, this is what the model should look like. It's clearly off from that. So I don't trust this model. This would not be a good model to launch. I would probably lose my job if I use this in real life. There's not a whole lot else I got to say. Take care and goodbye.